Okay, guys, we are just going to close this up. I don't know why these last slides didn't make it into the exported version. They just disappeared. So I've taken the occasion to add to the last 6 slides some comments at the end that hopefully help kind of bring into final focus the kind of the scope and the intentions of that I've had for teaching this course and my interests that have driven it. So let's get to it. The question here to pose is, having seen and gone through in the last 2 discussions, working with conflict data and working with climate data, what happens to our predictions, and more generally, what happens to our understanding of these problems when we move toward complexity or complex thinking? Kind of as Lee posed the question provocatively the other day, and I've been thinking a lot about it since he asked this question. He sort of said, what can we say about complexity theory? What kind of accomplishments, real world accomplishments, can we credit it for? And I've been doing a lot of thinking about that question since he asked it. I think it's a really good question for us, for the community to spend more time reflecting on and answering, because I think the point I would make is I think the rewards, the intellectual, the understanding, the deeper, richer understanding of social problems, wicked social problems like ours, conflict, poverty, development, and climate change, is so profound that we really must continue to engage and deepen our embrace of complex thinking, complexity systems, and complexity science more generally. I just think there's so much to gain and so very much to lose, that the stakes make it worth it. So that's what I want to do in these last couple of slides, just show you, kind of demonstrate in 2 different ways what I would say is the value of the move toward complexity thinking. There are those who say that you can't teach undergraduates complex systems theory. So I disagree. Now, you can't arm undergraduates that haven't had several semesters of advanced statistical analysis and computer modeling and things like that. You can't expect to have undergraduates walk away with an ability to write hundreds and hundreds of lines of code to create a complex adaptive systems model for predicting the outcomes of herder-farmer conflict in northern Nigeria. That's not reasonable to expect. But I think they're wrong when they say that we cannot teach undergraduates the concepts of complex thinking, how they help us embrace and engage with real-world problems, and in these final slides, the virtues of the move in the direction of complexity, and how that, what kind of payoffs are there. I think we can and should. So. To start answering that question of what do we get when we move towards complexity, I just kind of use the climate data and show what we can do and how it changes our understanding. Instead of, as we have done for the most part, say rely on, for example, CO2 level data to forecast future CO2 level data. Levels of CO2, or using the historical record of temperature to forecast temperature into the future. What we're going to do is, and because this is what we know, right? Climate systems are dynamical systems. The key the key dimensions and factors and elements of a climate system interact. And that it's that interaction that gives rise to chaos, and challenges for prediction, the sensitivity to initial conditions, and all of those things. So this is what these last slides do, is they put these factors together, and we'll see the outcome of doing so. So we've got on the bottom axis the CO2 levels, and we've got on the y-axis the temperature data. And moving in the direction of complexity is to analyze the interaction of these two forces, these two factors of a climate system. Doing so through the process of regression generates a model. And the model, r squared there is 0.7112. Remember, the r squared just tells us how good is that best fit line. It's called the best fit line because it's the best line you can draw to the data, but it doesn't mean it's necessarily a good line. The data could be so randomly distributed that there is no good line to draw. That 0.7 says, no, that's actually quite a good best fit line. Okay? And it is on that basis, of course, then that we can make predictions and forecasts, right? And doing so, with this analysis, the linear model makes a forecast of 448 parts per million of CO2 in the year 65, and an average monthly temperature change of 1.32 degrees Celsius. Now that's really quite important. The CO2 level prediction is pretty encouraging, because that's not at all far from where we are at present, which is about 420. And I should say that we need to be reducing these numbers. I'm certainly aware of that. But one thing we can continue to hope for, hopefully not naively, but hope based on experience, is that we can expect continued technological advancements in the area of carbon removal, carbon capture. So the reason I say, an increase of CO2 to 448 in 50 years is pretty encouraging is because even though we want to see the numbers falling, but in fact, as we've said before, they're actually been going up at a faster rate, sadly, in the 21st century than at the end of the 20th. This prediction indicates a leveling off of that rate of increase of CO2 emissions at a time in which we can expect that our technological capacity to remove carbon dioxide from the atmosphere will have continued to improve. So it is on that basis that 448 to me strikes me as something of an encouraging prediction. The 1.32 Celsius monthly average temperature change, however, is quite discouraging, because remember the number, 1.5 degrees. That's all we get to add to the global mean temperature. And what this says is in 50 years, you can expect the average monthly temperature change to be a positive 1.32. That means we'd be way past the total maximum of 1.5 degrees that the climate can sustain. So that's rather discouraging. So what about the shift to a polynomial, getting away from a linear equation? What do we get, right? So, we get an even more encouraging prediction or forecast. Same, almost identical CO2 forecast of 448.5 parts per million, but the monthly temperature change fell pretty considerably, pretty significantly, to 0.96 degrees Celsius, and that is lower than a lot of I think kind of contemporary estimates seem to suggest. So that had me wondering, how much confidence can I have in my analysis? Because I'll fully confess or concede that I'm not a statistician of great renown. It's just not the kind of work I do. I've always respected it, but it's just not the kind of work that I do. This is, in fact, I said before that one of the things that kind of hooked me up for a few days last week or a couple weeks ago was having to wait for colleagues to respond to my request to kind of analyze my analysis, because of something that happened on this this very page. Had me thinking I must have made a mistake. Right? So what was that mistake I feared, or on what basis did I think I had perhaps done something wrong? Well, The prediction, for one, is more optimistic than a lot of current predictions for temperature and CO2. So I look at my model, and the R squared, remember, the R squared, that 0.7169, simply tells us how well that line fits the data. Remember, it's a best fit line doesn't mean necessarily that it's a good fit. So R squared tells us it's a good fit, right? And the better the fit, the more reason we have for confidence that our prediction, our forecast is reasonable. But that's not enough alone, right? I needed to do, as statisticians do, I needed to assess my assessment a little further. So what I did was then run, what's called a Pearson's R, a correlation coefficient or a regression coefficient in this case, which just that small r, not the R squared, but the small r there, with the value of 0.84 is really quite high. If this weren't regression, if this was simply just a correlation analysis, that would just simply be the value of it would tell us the strength of the correlation. How much of an increase in CO2 is expected, how much of an increase in temperature can we expect given an X level of increase in CO2? The stronger, the higher that R, the closer to 1, the stronger the relationship, the stronger the correlation. And so an R of 0.84 is really quite high. It's a very strong relationship. And so on that basis, one can say that given the strength of the relationship between CO2 and temperature and the fit of the model to the data, we've got reason to feel some confidence that the 0.96 forecast is not unreasonable. Right? One final thing one needs to do is test those tests, right? And that's what the p-value there is for. Now, what the p-value is a measure of statistical significance. And what that means is it's sort of how you answer an important question, which is, how do I know that, say, the results that I've come up with, the data I used, the sampling, just didn't happen by chance, by complete freak luck, right? Said another way, in terms of the confidence intervals that I talked about, if I were to resample 100 times, what's the probability that, or if I were to just resample and do this analysis again, I use January data, remember. If I, January for 140 years, if I took February for 140 years, or whatever, if I just resampled, what is the probability that I'd come up with essentially the same, within a standard deviation, the same kind of outcome, same results? And that's what the p-value tells us, that the probability that my results have occurred by just random luck. Right? And in the academy, the minimum standard is 0.05, which means essentially that there's about a 5% chance that my results are the result of just random chance. Or conversely, if I were to do this again 95 times out of 100, I'd come up with basically the same result. So the minimum, as I say, is 0.05 to establish a level of statistical significance that you can say this isn't just a result of luck. That's the minimum. Now, better is 0.01, which basically says, right, 99 times out of 100. Resampling would give you the same results as I got this time, or one chance out of 100 that this is the result of just mere luck. And the gold standard in the academy is 0.001, which is essentially saying there's only one really time out of one chance out of 1,000 that the results that I've obtained occurred by luck, by chance, by hazard. If I were to do it again 999 times out of 1,000, I'd come up with essentially the same results. And so, I've achieved that standard. But there's an asterisk there. Why the asterisk, and why did I send my results off to colleagues that know this stuff better than I do? Is because the actual p-value that I got returned was just a wee bit smaller than that. smaller in the good, that's, smaller the better. And so, it was so much smaller that I felt certain I must have done something wrong, because I had never seen a p-value come back with this. And what p-value did I get? What gave me reason to assume that I must have done something wrong? That's what came back. That's 37 decimal point, 37 places to the right of the decimal. I've just never, ever seen that. I don't read and do stats much, so maybe it happens to others, but it certainly has never happened to me. And so that's why I said there's just no possible way that I've, I don't even know what that number is, but that's a very, very small number. And so it was on that basis that I had some colleagues do me the favor of looking at what I'd done, and they think it's good stuff. They think there's nothing wrong with my analysis. There is no mistake that generated a p-value like that. So they're pretty encouraged that my findings are pretty accurate and significant. So I think so it just gives me reason to feel kind of optimistic. That's not the worst possible forecast that we could have generated. So now, what about the chaos or the butterfly effect, right? What about the things we know about climate and conflict systems or what have you, is that they are sensitive to initial conditions. This is, if you remember, what gave rise to complex systems thinking in the first place, when by accident the analysis of climate data using early computers were generating results that didn't make any sense, and they finally figured out what had gone on. One research assistant had entered data rounding off to like 2 decimal points, and another had rounded off to 3, and just that little thing created outcome differences of enormous magnitude. And that's what we mean by sensitivity to initial conditions. So I wanted to kind of show what that looks like, or try to demonstrate the degree to which it's manifest here. So what I did was I went back into the data, CO2 and temperature data, and I just changed a few data points, just 4 years. I changed it in a very modest way, but in the good direction. I made CO2 levels modestly lower, 5%, in only 4 years. So 140 years, I think. So 136 years do not change, right? But 4 changed just by 5%. And I cooled off 4 data points by 8%. So again, 136 data points of temperature did not change, but 4 did. Early, these were early in the data set, by just a mere 8%. So very small change, and so on one level, one should perhaps not expect anything to be different. We're talking 280 data points in an analysis, and I've changed 8 by very small margins. So what do we get? The linear equation gives us essentially no change, right? We get a 50-year forecast of exactly the same CO2 level. And a temperature increase change of 1.325 as opposed to 1.32. So what I'm suggesting here is that the linear model, this bivariate linear equation, is just inadequately sensitive to reveal the way climate data have chaotic effects. You just can't pick it up. It's too blunt of an instrument, as it were, right? So what about the polynomial? Well, a little better. The equation that the polynomial equation is a good fit, and the prediction is 1.325. Remember, that's more than the 0.96 that I got without altering the initial conditions. Essentially the same CO2 forecast, but a hotter temperature forecast. So some manifestation of the sensitivity to initial conditions there, but really you must get into deeper complex modeling in order to generate or to reveal the way that climate factors are so sensitive to those initial conditions. So we come here to the final points that I want to raise. I want to take a few minutes to talk about in some ways, what I'm referring to here, we took on three social problems: conflict, poverty, and or underdevelopment, and climate change. And like the university itself, these three domains, these three problem areas or issue areas or problematiques have been for far too long siloed, disciplined, separate from each other. But I want us, hopefully, by now you already can know that these things are not separate worlds. These are very serious problems that are in fact connected to each other in ways that if we don't understand that, we can't intervene in ways to improve, and we throw one into the win column for Lee. So that's what I want us to try to do here in these final moments, is just kind of reveal what I'm calling the security climate development nexus, the interactivity, the recursive, mutually constitutive, mutually causal connections, relationships between and among these not discrete systems. It's a complex system of systems. Okay, we'll start by talking about the tragic way that the 21st century began, and that was with genocide in the Darfur region of Sudan in East Africa. This is a child's rendering of the attack by the Janjaweed on her village in Darfur. It was genocide, despite the UN's decision not to term it so. I don't know what else you'd call the slaughter of between 250 and 400,000 people of the Fur identity when those doing the murdering are making it perfectly clear that their intention is to kill in part or in whole the Fur people. They made it clear with even the graffiti they wrote on the burnt out walls of the villages they had attacked. And so it was genocide, and it was devastatingly horrific. So what can we come to know that's helpful by adopting the kind of complex thinking that is required? The first thing is I want to credit former Secretary General Ban KiMoon for being a very bright man, a very smart man. I'm just going to read you what he says. He says, almost invariably when we talk about Darfur, we do so in a conventional military political shorthand, right? It's basically, we say, an ethnic conflict that pits Arab militias against black rebels and farmers. Right? He's right. That's exactly the way. I remember reading every day in the paper how this was, the ethnic violence in Sudan between Arabs and sub-Saharan Africans was yada, yada, yada. And, it just so badly missed so much of what was absolutely essential to know and understand if you were going to understand the conflict in Darfur. He goes on, he says, we think of it in these classic military political terms, right? It's an ethnic conflict. But look at its roots, though, he says, and you discover more complex dynamics, right? He's a bit ahead of his time there. Amid the diverse social and political causes, which are key, he's not dismissing those, right? Among the social and political causes, the Darfur conflict began, meaning he sees that the root cause of the tragedy, the genocide in Darfur, began as an ecological crisis, arising at least in part from climate change. So let's think about what he's saying here. It became known as the first climate change conflict, certainly the first climate change genocide. Right? And it is through complexity modeling that we'll be able to see how this is so, right? Let's do that. We can begin, right, with the circumstance. Now, Syria's on the screen also. We're not going to talk about Syria, but we might do on Friday. But it's there because, one, I assume that Syria is a bit more present in your thinking than Darfur, but also very, very similar dynamics have been at work in Syria that I'm going to talk about here and with my model of Darfur. It begins with drought, right? The drought being the result of climate change, the increasingly frequent and increasingly intense water shortage, right? So that's where this starts. The root cause is the climate change results of drought. Now, what do we mean when we say root cause, right? Well, the outcome that we're most concerned with is the high level of violent death, right? So to say something is a root cause of something is to say that there's a fundamental, beneath all the other causal factors and things going on, the causal dynamics and the things that give rise to conflict escalation and that, independently and indirectly and directly lead to the outcome, the magnitude of the conflict. Beneath all of that is this fundamental relationship between a climate change driven drought and death, right? And it's Ban Ki-moon that helped the world better see this, which is something he deserves a great deal of credit for. So, how can a complex systems map help us see how this goes from the root cause of an ecological crisis to genocide? In the most general way, you have to understand that this is a conflict between herding or pastoralist community and farming communities, right? And for centuries, if not millennia, these herding and farming communities have sometimes been in conflict, but they've also just as often, if not more often, been in very harmonious, symbiotic relationships in which they trade or barter meat for milk and what have you. But it is the climate change that produces drought and growing desertification that means literally the ground beneath their feet is failing them, and it, in doing so, transforms the relationship between these herding and farming communities from a potentially symbiotic relationship to a genocidal, murderous relationship. How does that unfold, right? How do we go from the root cause to an understanding of the interplay of the multiple factors that finally give rise to genocide so that we could possibly intervene, right? Well, the first thing you want to know, right, is that drought sets people in motion, right? People move when drought happens. Farmers move looking for ground that can actually grow something, right? Ground that's not just cracked and broken. And pastoralists do the same. They must move to find land that is producing enough vegetation to feed their cattle. So the drought sets human beings, human communities in motion. And that movement creates a new level and new locations of competition for the thing they both need, land that's not drought-stricken. Right? So farmers and pastoralists are now meeting each other more frequently in these increasingly rare spaces where land might sustain them, and that means the competition between them is growing more and more intense, reaching the level, obviously, of survival. Right? Now, I just said, so what's next? And we're tempted, I think, naturally, cognitively, to continue to ask those kinds of what happens next questions. But if we do so, if we continue to think in that linear way, right, we miss some of the most important things about dynamical systems, right? And that's the simultaneity of factors and feedback loops and attractors. And I hope I've come up with a way to kind of a new way of helping you understand attractors. So the question ought not necessarily be, okay, then what happened, right? Because that would miss the way dynamical systems work, and that's the simultaneity of multiplicity of factors. So don't take your eye off the map, the whole map, right? If you look at the one result, the pastoral movement continues to increase, right? The herders continue to move. Or if you focus on the declining agricultural productivity result, you miss the pastoral movement factor. So you've got to see them all at the same time, but also individually, if such a thing is possible, right? So the simultaneity that I tried to show there, right, is essential to, what it is that complex thinking and systems mapping does for us, right? So the land degradation, these are outcomes that are moving us toward that death, right? Cattle movement, farming movement, increasing the land degradation problem, decreasing agricultural productivity, further increasing ethnic tensions, because the herding and farming communities are of different ethnic groups. And what has happened, and what I discovered in my early dissertation research when these things start to happen, is they start talking about each other in ways that reflect their ethnic difference rather than their sort of occupational difference. They don't talk about each other as herders and farmers anymore. They talk about each other by their ethnic label. I call that ethnogenesis. And that's what's happening there. The ethnic tensions are getting worse, and from there, right, it's not, again, okay, what thing happens next? Because again, it's about simultaneity, right, and recursive. Wow, a lot happens, right? So these orange circles, right, reflect kind of the results or emergent properties in a complex system, right? The increased social instability or decreased social stability is an emergent property that results from what's been going on, the interactions of those factors that we've discussed. Civil war is an emergent property. The violent conflict that erupts is a property that emerges from this dynamical system. Now notice that there are now two circles around some things, right? And that's because, causality in a complex systems model is not unidirectional, right? Causal relationships go multiple directions in time and in space. And so what I've tried to show here is what an attractor might be in a conflict system like this. So the ones now with two circles around them would be good to see or think of as attractors. Take the ethnic tensions, because you see that death at the bottom loops back to ethnic tension, right? That's what we want to understand, is that the way these systems work is that some parts of them continue to worsen, deepen, intensify. We call them nodes, we call them attractors, we call them black holes of feedback loops, but they're the elements of a conflict in this case, around which intensification, escalation, can be identified, can be observed, right? The agricultural productivity decline continues to decline because of the things going on in this conflict system. The drought reduced agricultural productivity, but so did the search for new land, and the use of new land more intensely reduces it. So does the conflict on the land, the burning, the bombing reduces further, and that further reduces the tensions around land and the need for land. So those with two circles now can be seen as what we refer to as conflict attractors, right? Those elements of the conflict dynamical system that must be understood as core loci of escalation of conflict. It's there that we must intervene if we're going to break the cycle of escalation. Right? And then as we move forward, as the system continues, it just generates further and further levels of that root result, which is death. I hope that helps us see not just how a conflict system works, but also the climate conflict connection very clearly, right? the root cause between drought and death is clear, but that alone is quite important, but not enough to understand the way that we need to understand a conflict so that we can hopefully intervene. So finally, we'll talk about what we're doing in the broadest sense, right? I want us to understand first that it is not malevolence that often gives rise to the worst horrors, right? But basic human needs in conflict, right? We all have, both as individuals and societies, we have certain basic human needs. We have need for food security, a stable, good, reliable supply of nourishment. Same for water. We have water security, human needs, right? Water for drinking, water for our animals, water for our crops, water for our bathing. We have a basic water security need as individuals and as communities, right? And we have energy security needs. We need a stable, secure supply of the energy, irrespective of the level of development and the form of energy that we might be utilizing. We need a secure, stable supply of energy to do the things that we do in life, cook and what have you. Those aren't malevolent factors. Those are basic human needs, right? What we need to then consider is where we seek or where we can hope to satisfy our basic human needs for food, energy, and water. And that's the ecosystem. And that's why, that pale blue dot that Carl Sagan was telling us about is, in his view, ever more precious when seen from such a distance, because it does become very clear that it's just a tiny, fragile little place. Right? And we don't think of it as a tiny, fragile little place too often. But it is where it's the only place we can hope to find that offers what we need to satisfy our basic human needs for food, energy, and water. Right? The resources, the water, the land, and the energy resources that the ecosystem provides us are there. They must be managed in a way that can satisfy individuals in community needs, because if they are not, we get Darfur. Okay? That's what the Darfur map, I think, hopefully teaches us. Okay? And to mention Eleanor Ostrom again, she won the Nobel Prize, I think, because ultimately she showed us that it is possible to manage our resources, our ecosystem resources, common pool water resources, fisheries, forests, you name it, right? In a way that satisfies the needs of those using or with access to those systems, those resources. It does not require, as she showed so many times, some strong authoritarian state to force people into behaving properly. It is possible for societies to self-govern their resources that are so fragile and finite. And it was the irrefutable evidence that she compiled over the years, from a graduate student in Los Angeles doing water resources to her legions of researchers going around the world and showing the same. It is possible to effectively govern the commons, okay, and therefore satisfy our basic human needs. The failure to do so, when we do not, we know what the results are. Guaranteed, it is more conflict, leading to further environmental destruction, which only reverses the development progress we've made. It has been said that war is civil war in reverse, and you can see that most tragically in satellite imagery of the Darfur region, where it's just now it almost resembles an extraterrestrial planetary space of burnt out, cratered remains of a place where people once lived. This is what we can know. This is what we can do with what we know. It is now really a matter of choice. Thank you.